Okay. Last time we started talking about parametric equations, and the difference is that we have instead of having y as a variable of x, now we have a new parameter t, which I like you guys to think as time, and we have the x and the y, and both x and y are now going to be functions of t, of the time t. And let me go to the page and I'll show you what we were working on last time. We had this parametric equation for cosine 2 pi t, for sine 2 pi t. And so those graphs look like this. That's the cosine one, and that's the sine. And we saw that when we were describing it like this, it looked like a circle or something resembling a circle. And I even show you an animation from Mathematica. I'll show it to you again. And that kind of tells you that that's indeed the case, that it does look like a circle. So let's take a look at it. Where did I leave that file? Right here. Yes. So as you can see, I put the same function here for cosine 2 pi t, for sine 2 pi t. And as I slide it, it describes a circle, right? Or it looks like a circle. And a circle of radius 4, to be more precise, center at the origin. Okay? So we're going to check how we can verify that this graph is indeed a circle. And another thing that I want you to check here is that this is not the graph of a function, right? So this circle fails the vertical line test. If you pick a line, say the line x equals 2, it crosses the graph in 2 points, and that's okay. Parametric equations are way more flexible than regular graphs. We can describe a variety of other curves. Okay, so let's go back to the page and talk about why this is indeed a circle. Okay, so this is what we have. We have this equation, 4 cosine 2 pi t, y is 4 sine 2 pi t. And the idea here is to think of something that relates cosine and sine, right? And what is it? Well, we have this beautiful identity, the classical identity that we use all the time that relates sine and cosine. And that one is that sine squared plus cosine squared equals 1. So let's use that one here. And what we want to do is then square these numbers. So what would be x squared? Let's fit it in here. X squared. When I do x squared, that would be 16 cosine squared of 2 pi t. And when I do y squared, that will be 6 squared sine squared of 2 pi t. And then what's x squared plus y squared? When I factor the 16, we get our expression that I was telling you about, sine squared plus cosine squared, and we know that's 1. So by eliminating the parameter in this way, we got this equation, x squared plus y squared equals 16. And we're well aware what that is, right? That's exactly the graph of a circle, center at the origin with radius 4 squared. So it's exactly this guy over here where the radius is 4. So from -4 to 4 here, -4 to 4. Exactly like the one that I showed you in my previous animation. All right? So that's a way. So it's important to remember this one because it will happen at other times. So in general, if you use cosine and sine, cosine for x and sine for y, you get a circle, right? And if you want a bigger circle, you just multiply by the appropriate parameter here as the radius. So if you put a 4 here, it will be of radius 4. If you put a 10, it will be radius 10, and so on. Okay. Fantastic. So now let's talk about the next important things we should be able to parameterize, which are lines. So parameterization of lines. And they all look, they're kind of straightforward lines. So here is how you can usually parameterize lines. They all look like this. The x is some special point x0, and then some other constant here, a times t, and over here some constant b times t, where the t ranges from negative infinity to infinity. This is how you parameterize lines. And the picture that you should have in mind is the following. This line will go through the point x0, y0. So somewhere over here is the point x0, y0, which you would get when t is 0. See, if you plug 0 here, if you make t equals 0 here, you don't get anything here. You get x0, y0. So you definitely go through this point. And then you have a line, and this a is essentially how much the x coordinate is increasing per unit of time. So if you go 1 unit this way, so if you go x0 plus 1, you go a in this direction. And if you go y0 plus 1, so if you put over here t equals 1, you go b. So after 1 second, so to speak, you move a in this direction and b in this direction. So this is when t equals 1. And this is when t equals 0. So b over a is then the slope. So the slope is b over a. All right? Is that clear? So that's a pretty easy way to go from regular lines that we know. So if you know a point and a slope, you can write these parametric equations. And also, if I give you these parametric equations, you can come up with the other one. I'll show you an example. So here's first example. So say I give you this line, the line y minus, I'm just inventing this, y minus 5 equals 2/3 times x minus 2, right? How can I come up with parametric equations for this one? Some parametric equations, by the way, because there are several, right? You can start the line in different places. You can go at different speeds, right? There's many different ways you can do it. But this is kind of like the canonical one, the straightforward one of doing it. So here, see what's a point on this line? A point that for sure is on this line is when x is 2 and when y is 5, right? And what is the slope? Well, the slope is 2/3, right? So I can go back and let me see if I can put it on the same screen. Yeah, right? I can remember this way of doing it. So here are my parametric equations. Here are my parametric equations. X will be the x0, which is 2, plus the a, and the a is the one in the bottom. So 3t. And y will be this guy over here, 5, plus the one on the top, 2t. That's it. Pretty straightforward, right? Now, going the other way around is even easier. The only thing you need to do is eliminate the parameters. So to go back to the original line, all you need to do is solve for t and plug one into the other. So let's do example 3, which is exactly about this. So part A says, consider the parametric equations x equals negative 2 plus 3t, y equals 4 minus 6t. T between negative infinity and infinity. So the entire range. Find the slope intercept form of the line. All right. A little bit to the corner. Okay. How do we do it? Like I said, this is the pretty straightforward way of doing things. So all you need to do is solve for one of these and plug into the other one. It doesn't matter which one you pick. So I'm going to pick the top one. So solve for t. So 3t equals x plus 2, which means t equals x plus 2 divided by 3. Correct? And then plug into the other one. And when I do that, I get y equals 4 minus 6, and instead of t, x plus 2 divided by 3. And that's it. All you need to do now is simplify. So what is this? This is y equals 4 minus 6 divided by 3. That's 2. Parentheses x plus 2. So this is 4 minus 2x minus 4. So this is actually the line y equals negative 2x. We are done, right? That's the line that passes through the origin and has a slope negative 2. So slope is negative 2 and goes through the origin. So that's the y intercept. Okay. Next, part B. It says, find two pairs of parametric equations. Parametric equations for the line with slope 1/3 that passes through two comma 1. Okay, so like we said, right, tons of ways of doing this, tons of ways. So the formula, maybe I'll put it back. Where is it? Right here, right? So if we have a point, we put it here. And if we have the slope, we put it here. It's as simple as that. So in this case, we have slope 1/3 and passes through 2 comma 1. So it's going to be, so here and they're asking us for two different ones. So I'll show you in a moment how we can do them. So 2 comma 1, the point is 2 comma 1, so this go here. And the way we can make them different is by writing the slope in a different way. So the slope 1/3, we can also write it as, I don't know, 2/6 or 3/9, right? So the slope, let's do it with 1/3. If we do it with 1/3, remember the one in the top. So A, it has the denominator. So X has the denominator. So in this case, the denominator is 3. So this would be 2 plus 3 times t, and 1, and y has the top, in this case 1, so 1 plus t. Or what we can do is we can use a different way of the slope. Instead of using slope 1/3, we can think of the slope 2/6 or 3/9, right? So I'm going to use 2/6. So then I make this 2, and then I make this 6, right? And here's what I was telling you. These are, this is the same line. It's the same line that we're describing, but as a picture. As a picture, the same line. But as a movie, things are happening differently here. What is different is that this one is going twice as fast. So here we're drawing the line twice as fast as over here, right? So look, this guy after 1 second is already at 8 and at 3. And this one in 1 second is at 5, 2. So this one is going twice as fast. Does that make sense? That it is the same line, only travel like quickly, way faster than the other one. All right? Okay, and one more thing is the next example, which is what if you don't want the entire line? What if you only want a little bit of a line, like a segment from one point to another point? So let's talk about that one. And I'll actually show you different ways of doing it. So this is example C. Find parametric equations for the segment, for the line segment from the point P 47 to Q 2, -3. All right, and I'm gonna show you two different ways of doing it. One way is for us to simply do the line and then figure out from where to where, right? So that's one way. So solution 1, find the line and then figure out beginning and end. So let me do it this one first. So to do it with the line, so I want this to be the point. So it will be 4 and 7 because I'm starting from P 4, 7 and I'm finishing in 2, -3. So I need to have the slope now, right? So what is the slope from here to here? Well, the slope, remember, is the rise divided by the run. So the rise would be from -3 to 7. Divided by the run from 2 to -4. So this is -10 over -2. So that's 5. 5 over 1, right? So then the x goes with the one in the bottom. So like this, and the y goes with the one on the top, like this. All right. Now, if we put t from -infinity to infinity, the entire thing, then it's going to be all the line. But I don't want all the line. I want only the line segment, right? So I already know that when we plug t equals 0, if t equals 0, then x comma y becomes 4, 7, and that's P, the point P. Now, the only thing I need to do is find out what t gives me the point Q. So find t such that x comma y equals Q, and Q is 2, -3. And as a matter of fact, you can only use, you don't need both equations. With one of them will work. So you can use the x only. So the x is 4 plus t. And I want 4 plus t to be equal to 2. So then now I solve for t. So t is -2. So this one over here will be what I want. And all I need is for t to be between 0 and -2. -2 to 0. All right, is that clear? That's how we do it. Now, here's a different way. Here is a different way. Different way is to simply specify. So solution 2. And this one you can even make it so that you can have it to be at one point at whatever number of seconds and the other point at whatever other number of seconds. So suppose that I want, so solution 2, I want the point P at 0 seconds. And Q, the point 2, -3 at 1 second. How can I make it so that happens? And it's easy too. All I need to do is find out. So the 0 seconds parts, we got it. It looks like this. And then all we need to do is solve for A and B. So we already know that it looks like this. Is 4 plus A times T, and is 7 plus B times T. And what I want is that when I plug 1 second, I get 2 on -3. So plug T equals 1. What does it give? It gives 4 plus A, and this one goes 7 plus B. And I want this to be 2, and then I want this to be -3. So now I can find out what are A and B. So from here, A is 2 minus 4, that's -2, and B is -3 minus 7, that's -10. So that's my answer to the problem. My answer will be 4 minus 2T and 7 minus 7T. And now you can check what happens when you do 1 second. When you do T equals 1, you plug it here, you get 4 minus 2, that's 2. When you plug T equals 1 here, you get 7 minus 10, that's -3. All right? So that's a second way of doing this. All right. And this is useful if you want to do things that are a bit more complicated, which is our next example. So how we can parameterize other things. Well, I'm going to show you the next example 4.
Professor?
Yes.
So the new one we just found, equals the last one we did, but it grows faster.
Yeah, good question. So you're asking how is this one compared to this one? How are they similar or different, right?
Yeah.
And see, here's the difference. This one starts at, when T is -2, you are at the point Q. So this one, if I were to draw the picture for this one, it would be like this. Let me see if I can put the picture here. It would be that it starts at 2, -3. 1, 2, 1, 2, 3. This is Q. And it finishes at 4,7. 3, 4. 1, 2, 3, 4, 5, 6, 7. All the way over here is P. So this one starts here at -2. When T is -2, we're here. And then it goes this way. And it finishes at T equals 0. So, and it goes this way. So it goes from Q to P. That's the one we did here. And then the second one we did, let me draw it over here. Goes 1, 2, 3, 4, and over here 1, 2, 3. So this is still Q, and here's P. This one starts right here at P, and then after 1 second, we are in Q. So you are right that the second one goes twice as fast, but actually it also goes in the opposite direction. And I don't know if you had realized that. Yes? So as a segment, as the picture that you get when it's all done, you get the same picture. It's just a segment. But the way it was drawn is different. This one was drawn from here to here, 0 seconds, 1 second. And this one was drawn this way, starting here at -2 and then 2 seconds. So slowly, right? Slower. Does that answer your question, Michael?
Yeah.
Good. All right. So let's do example 4, part C. Right, let me probably show it on the book. All right. So we want part C right here. It says parameterize the piecewise linear path connecting P -2, 0 to Q 0,3 to R 4,0 in that order, where the parameter varies over the interval 0 less than or equal T less than or equal to 2. So I'm going to start by drawing the picture of what we want. So it's a couple of segments, right? So let's see. If I want -2, 0, 3, 4, 0. Okay, so -2, 0 from 0, 3 to 0, 3. So this is P, Q, and then all the way to 4, 0. And let me switch back to the page. So we want to go from here to here, and then from here to here, right? And probably the better way to do it is if we, break it down by seconds, so that we maybe go from here to here in 1 second, and then from here to here in 1 second, right? And that would be the easiest because we've already sort of figured out our way of doing things, right? So in general, let's start with the first part. So the first part, we want x to start right here at -2 and at 0, and then finish right here. So AT plus BT, and we want to be here at 1 second. All right. So we want to be here at 1 second. So then when we plug 1, we should have x and y to be 0,3. So -2 plus a should be 0, and 0 plus 3b should be 3. So from here we get that a is 2 and b is 1. All right, and that's between 0 and 1. Okay, so let's write down the part that we have so far. The part that we have so far is -2 plus 2t and t between 0 and 1. And hold on a sec. Why did I put 3 here? And t equals 1. There's something wrong here, right? This should be just b. My bad. So this should be 3. So this is 3t. And this is 0 less than or equal to t less than or equal to 1. Okay? That's the first part. That's only going from here to here. Now, how do we go from here to here? And this time we want it to be from 1 second to 2 seconds. So we wanted it to be at 1 second right here. So so for the second part, so this time we want x and y to be, and so I cannot use now same as before. I cannot write simply 0 and 3 here, because then that would be at 0 seconds, right? Or I can if I do the following. So look, this is the trick. The trick is to write still the same numbers here, but now we're gonna multiply not by t, but by t minus 1. Do you see why I'm doing this? I am doing this so that when you plug 1, what happens when I plug 1? 1 minus 1, 0, 1 minus 1, 0. Then I don't have this. And then what I have is 0, 3, which is what I want to be here, right? We want to start at Q. That's exactly what I want. So t minus 1 is what we should put here. And then we find out how to finish at R by plugging 2. So it's the same thing. We plug t equals 2. We should have x, y, be 4, 0. That's what we should get. All right. So now we'll plug it, and what we get is x equals 0 plus a times 2 minus 1, and this should be 4. And y is 3 plus b times 2 minus 1, and that should be 0. So from here, a is 4, and b is negative 3. So here's my answer. My answer is x equals a, which is 4, so it's 4 times t minus 1, and y, which is negative 3, so it's 3 plus, which is minus, because it's negative 3, times t minus 1. And this is between 1 and 2. And we are done. So the answer are these two together. This is the between 0 and 1 seconds, and this is between 1 and 2 seconds. If you want to write them together, you can write them like this. So x is negative 2 plus 2t if 0 less than or equal to t less than or equal to 1, or 4 times t minus 1 if 1 less than or equal to t less than 2. And y is negative, y is 3t if 0 less than or equals t less than or equal 1, or 3 minus 3 parentheses t minus 1 if 1 less than or equal t less than or equal to 2. Okay, and that's it. That's our parametrization of that arc that went here and then there, right? And I hope you can see that we can keep doing this. If it was a longer polygonal, like pop, 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 several points, we can keep doing it, right? From 0 to 1, 1 to 2, 2 to 3, 3 to 4. If we can go a second at a time, we can even change. Maybe we want one part to go faster than the others, right? This one take, or slower, from here to here, take 10 seconds, but then half a second. And we could do that too. You get to decide all of that, right? There's a lot of possible variability here, okay? Good. I'm gonna show you another one, which this time from my, so it's from the, I mean, let's go to the book. I'll show it to you on the book, and then I'll show you my animation that I prepared for this. So in the book, next page, we have a special curve that we'll see later on. It's called a cycloid, and it has a bunch of nice properties. We'll talk more about this cycloid later on, but in particular is the graph that you obtain when you roll a circle. Think of a wheel, like a bicycle wheel, right? So imagine that you have a bicycle like the one you're seeing on the picture right now, and the bicycle has a light in one attached to the edge of the wheel. And so what happens to the light as you move, as the bicycle rolls, right? as the wheel of the bicycle rolls, the light describes some curve. And that curve is called a cycloid. And it has a bunch of interesting properties that we'll talk about later on. And I wish we had time to even discover what the formula for this particular cycloid is. But let me show you my little animation so that you see it. And this will also give you an idea how, using parametric equations, you can describe curves that are way more interesting. So here is my cycloid animation. All right, so that's the circle where it starts, and right now imagine that the spoke, the light, is right at the origin. So as I start rolling the wheel, the light describes that blue path that you see, right? And once the wheel has done half a revolution, now the light is at the top, right? And then as the wheel continues to roll, now the light comes down. And once the wheel does a complete revolution, the light is back all the way down. And then the entire thing repeats, right? So if I keep going, then it does the same thing again. Okay? Let me just go back and forth. Let's just have it play here. Okay, so so that's a specific graph, and it's given by, maybe we show the equation here. So in this case, I made it the circle of radius 1. And if you want the circle of radius 1, then it's given by this parametric equation. The x coordinate is t minus sine t, and the y coordinate is 1 minus cosine t. Okay? So it's an interesting equation and an interesting graph. We'll see actually many more like this coming up soon. But enough of looking at pictures. This is, after all, a class about calculus, right? So we should start talking about calculus characteristics of these objects. In particular, the first thing we want to talk about is, well, the derivative, right? If we have a parametric curve, if we have some curve described parametrically, so if I have something like this, let me do a picture here, maybe like the cycloid, right? So we have maybe this cycloid that we were doing, right? It's a curve like this. And I have a particular time here, like say t equals, I don't know, 1, I don't know where t is. Well, I want to know how I can find the slope of the tangent line, right? So what is the slope of the tangent line? What is the slope of the tangent line, right? Because we want to find out to find the equation of the tangent line, we need the slope, right? We already have a point, that's easy. So we would like to find the slope. And what is the slope in general? If we know that is simply the derivative. If it's a regular function, is the derivative. So we know that if y is a function of x, then the slope of the tangent line at x0, y0 is, what is it? The derivative, right? Is, let me write it like this, dy dx at x0, y0, or f prime when you plug x0, right? This is the derivative. Now, the problem is we don't have a function like this right now. Right now, we don't have y equals f of x. We have y equals, in fact, let me change this to capital F so there's no confusion. Right now, we don't have that. What we have is this. We have x is f of t and y is g of t. That's what we have, right? But here's the thing, though. What we can do is we can figure out a formula for what we want in the following way. See, using the chain rule. So from here, if we think of y as a function of x, then to figure out what is the derivative of y with respect to x, we can do the following, right? When we do the derivative of y, I want to do the derivative of, yeah, of y with respect to t, right? So x is a function of t and y is a function of t, but I'm also thinking of y as a function of x. So if I do the derivative of y with respect to t using the chain rule, well, let's see, y is a function of x. So it will be the derivative of y with respect to x, chain rule, times the derivative of x with respect to t, right? That's the chain rule. And if this happens by the chain rule, what I can do now is solve for what I want. This is what I want. So if we solve for dy dx, gives dy dt over dx dt. Or in other words, this is g prime over f prime. And you've got to put the t, you got to put t0, the time at the point that you want. So this is the general formula for the derivative, but if you want to find a specific, so if you want to plug the derivative at a specific point, you got to plug the t of where the time at which that point was the outcome of both the x and the y. Okay, so this is the important thing to remember, the derivative of dy dx. And let's see an example about finding slopes. So here's example 6. Example 6. Find dy dx. That's the instruction. And what do we have? Part A, x equals f of t is t, y equals g of t equals 2 root t for t greater than or equals 0. All right. So what is this one? Oh, and there's more. It says find dy dx and find the points where there are horizontal or vertical tangent lines. Or vertical tangent lines. Okay, good. So we already know how to do it. It's right here. So if we want dy dx, what we do is dy dt over dx dt. So we need to do the derivative of y with respect to t. And so we need to do 2 root t, the derivative of that, divided by t, the derivative of that, right? And this is like 2t to the 1/2. So this is the 1/2 comes down. So it's t to the negative 1/2. And this one is 1. So it's just 1 over root t is the derivative. All right? And provided, of course, we cannot divide by 0. So this is for t greater than 0. For t equals 0 doesn't work. Okay? So that's the first part. We found the derivative. Now, how can we find horizontal tangent lines and how can we find vertical tangent lines? Well, horizontal tangent lines happen when the slope is 0, right? And vertical tangent lines happens when the lines are vertical and vertical lines have no slope. It would be that the slope of that line is infinity or negative infinity, it's undefined, right? So you will find those where the denominator, where this expression is undefined because the denominator is 0, right? And the numerator is not 0. So horizontal tangent lines happen when dy dx is 0. In this case, this is never 0 because if this is 1 over something, that's never going to be 0. No solution here. Vertical tangent lines when dy dx is undefined because the denominator is 0, but not the numerator. That's important because if you get 0 over 0, it may be something else, right? And when does that happen? Here it happens when t is 0. Here it happens when t is 0. And we'll show a picture in just a moment, but before I show the picture, I want to do part B. So it's the same question, but now for part B, we have x equals 4 cosine t, y equals 16 sine t, and t between 0 and 2 pi. Okay, let's work it out. So dy dx is dy dt, dy dt over dx dt. The derivative of y with respect to t would be this function, the derivative, and divided by this one. This is 16 cosine t. This is 4 negative 4 sine t. So this becomes negative 4 cotangent t, right? And that's it. Now, what about horizontal tangent line? All right. Horizontal tangent lines happen when the numerator is 0 and the denominator is not. So horizontal tangent lines when 16 cosine t is 0, right? And vertical tangent lines when 4 sine t is 0. So this happens between 0 and 2 pi. The cosine is 0 when t is pi over 2 or 3 pi over 2. And this one happens when t is 0 or pi or 2 pi. Okay, so that's the answer to that one. Let me show you a page from the book. So the first equation that we were talking about was this half piece of parabola. And as you can tell, just like we said, there is no horizontal tangent line. And there is one vertical tangent line right here at 0. Okay, For the second example that we did, the picture that is described there is an ellipse. Is this ellipse over here. And this ellipse has effectively two horizontal tangent lines. One of them happens when t is pi over 2, right here. The other one happens when t is 3 pi over 2. And it has two vertical lines as well. One when t is pi, and the other when t is 0, or 2 pi, because 2 pi was the same as 0. It was cyclic there, so we that's the point where we started, and it finishes right at the same point. So either 0 or 2 pi, both of them work the same way. Okay? All right. Questions? All right. Let's move on to the next topic. So the next topic here is arc length. So how can we calculate the length of a parametric curve? All right, and I'm gonna go to the book again, and I don't want to derive the formula again. We did it already last semester when we studied arc length of specific curves. And so I'm just gonna show a little bit of the pages of the book of how we could derive the formula, and instead what I want to do is an example. So let's take a look at the book again and look at this its next page, so that I can tell you a little bit about how we could derive the formula for arc length. And the idea is the same. Slice into a lot of little pieces, in this case, the interval A to B, and then approximate each one of the little pieces. So this picture over here has essentially everything that we need. So imagine that we have a parametric curve like the one you see on the screen right now. And it starts over here at f of A, g of A, and it finishes over here at f of B, g of B. And what we're going to do is we're going to split the time from A to B into little pieces, little intervals of time. Time 1, time 2, time 3, time 4, etc. And then we look at the points. So this is at time 1, this is what happens at time 2, time 3, time 4, etc. And then instead of looking at the curve that we describe here, we're going to imagine that we have a straight line segment in between two consecutive points. That's a picture you see right here on the right. Right here on the right, you see that we're using this, instead of the curve, we're going to use this red segment as an approximation. And we want to know how long this is. And how long that is, well, this is the horizontally is the change in y, in x, and vertically is the change in y. So by the Pythagorean theorem, this length is the square root of the length in the change in x squared plus the length in y squared. All right, so that's the little thing we want to add. And then we want to add up all of them, all of these. So it becomes this sum over here. That's our approximation. This sum over here, right? The one that we have right here in the center. Okay. Now the idea is then to look this like a Riemann sum, so that it can be translated into an integral. That's what we did last semester. And we're going to do it the same way. The way we can make it into a Riemann sum is by remembering that this change in x is the change in x, we're using the function f, and then using the mean value theorem, we can divide that and by the real change in t. That's important because we want to relate it to t, times the derivative for a point that is in between tk minus 1 and tk, right? So we get this identity over here, right? So the change in x is the derivative for some point in between times the change in t. And the same thing happens for the y, only with a different, probably a different time. But when we plug it in, you can then factor out the change in t, and that's fantastic because now it looks like a Riemann sum. right? Now this one in the center is a Riemann sum, and Riemann sums are great because when n goes to infinity, they become an integral. And this is really the only thing. If you were having trouble following this explanation, don't worry. The only important thing you need to remember is this formula in the very bottom. So the arc length formula from t equals a to t equals b, the length of the curve is that one over there, the integral from a to b of the square root of f prime square plus g prime square. That's all you need to remember, where f and g are the parametric functions for x and y. I'll show it on the screen in just a moment. And then to finish the class, we'll do an example about that. So this is what we were talking about. The function to figure out the arc length is the derivative square of f plus the derivative square of g. All right. So let's do a specific example. We'll do, well, let's start with example 7, and then maybe we'll do example 8 next class. So here's example 7. It says, show that the circumference of a circle. So find the length, find the arc length of the circle with equations x equals a cosine t, y equals a sine t, where t goes between 0 and 2 pi. Right? That's how we can parameterize a circle with cosine and sine. That's like the one that I showed you in my animation at the beginning of today's class. So how do we do it? Well, here's how we do it. We need to integrate from 0 to 2 pi, right? The square root of, what's the derivative of the x function? Well, the derivative of a cosine t is negative a sine t. We're going to square that. Then plus the derivative of the y function. The derivative of the y function is a cosine t. Like that. And here we're super lucky because this simplifies incredibly, right? It's a squared. The negative sign goes away because we're squaring it. And then we get sine squared t plus cosine squared t. And we're well aware that this is 1. So this becomes the integral from 0 to 2 pi of the square root of a squared. So that's just a times the integral from 0 to 2 pi of dt. So that's just t from 0 to 2 pi. So that's 2 pi a minus 2 pi 0. So it's 2 pi a, which we kind of knew, right? The perimeter of a circle of radius a is 2 pi a. Okay, so let's at least start the second question. The second question is about finding the arc length, example 8. Finding the arc length of an asteroid. Find the length of an asteroid given by, here we go, the x is a cosine cube t, and the y is a sine cube t, and this ranges from 0 to 2 pi. And it's an interesting curve. Let me show it to you right here. You can also be described by a point that rotates. If you've ever done one of these, used to be toys for little children where you have like a circle, and you have little circles that you can roll inside the other circle, and you could put a pen through one little hole and see what kind of shapes you draw when you draw go all the way around. A spirograph, I think it was called. Well, this is an example of one of those curves. If you have a little circle here and rotating inside a bigger one, and you see what happens with one of the points, it describes this curve. It's called an asteroid. It looks like this. And we want to find out the arc length of it. And we just want to write down the integral that gives the answer, and we'll do it next time. All right, so just to finish today's class, let's write down what integral will be the length of this one. So here's the formula from 0 to 2 pi. It will be the derivative of x with respect to t plus the derivative of y with respect to t, right? So all we need to do is figure out what these two derivatives are. So what is the derivative of a cosine cube of t? The 3 comes down, so it's 3a cosine square times the derivative of cosine, which is negative sine. Plus, and here the same thing, the 3 comes down, multiplies the a sine square, and the derivative of sine is cosine, and we square everything. So is that one over here. This negative sign will not matter when we square it. So it's going to be, let's see, 9a squared cosine to the 4th sine squared plus 9a squared sine to the 4th cosine squared. And we can factor a bunch of things here. Let's do it. We can factor at a 9 and a square, a sine square, and a cosine square. And the stuff that remains is cosine square plus sine square, which is 1. So the integral, and now everything here is positive, so we can take it out. So the 9, we can take it out, and this becomes 3a sine t cosine t in absolute value dt. And we'll continue from here next time. So we still need to evaluate this integral to find out what the length is, but at least we know what integral is the one that represents the arc length of this function. All right, so I'm gonna stop right here. Are there any questions? Okay, if not, I'll see you guys next week. All right, see you guys next week.